Okay, so basically this problem is about the twin paradox in proper time. It talks about two twins, Brunhilde, who is staying on Earth, not moving at all, and Hildegard, who is moving to a faraway star system, like a star, and then all the way back the same length. So
so if I'm Brunhilde and the guy is Hildegard, so I'm going to be standing still at Earth, and then Hildegard will be gone, so bye. And then come back, and then basically I work.
Alright, that's good. You can pass it. Alright, so here we have a problem where Brunhilde stands as they explained, and then Hildegard moves with a very fast speed and then comes back to Earth. So we have a distance of L given, and that's the distance between Earth and another planet that Hildegard goes. So we know that the first thing we know that distance equals speed times time. And the first question asks, what's the time t that passes for Brunhilde if the distance to the star is L? So also the another given equation here is that Hildegard's speed, and we know that Hildegard's speed is beta c. C is the speed of time and beta is the fraction. So Hildegard moves with a speed of beta c, and that's also given. So for Brunhilde, for number one, let's say time of Brunhilde that the Brunhilde experience is during the flight and back is distance, which is 2L, because it comes back and goes there and comes back, over distance over velocity, which is beta c, which c is the speed of time. And that's basically all we have for number one. It asks for the time that Brunhilde experienced. Okay, so question number two. Question number two asks for how much time passes for Hildegard according to Brunhilde. So what we learned from class about time dilation is this equation, that t that's in initial reference is equal to the th over 1 minus v squared over c squared. So we use this very equation and solve for t of Hildegard. So th equals time Brunhilde over, time Brunhilde times 1 minus v squared over c squared. So we just plug it in. th equals 2l over vc times 1 minus, so v, we know velocity is beta c, so it's v squared c squared over c squared. So c squared cancel out, and okay, 2l over beta c square root of 1 minus beta squared. And when we're solving the problems with time dilation, we assume that c equals 1. It makes things much easier. So if c equals 1, it's just 2l over b, beta times square root of 1 minus beta squared. So that's the equation for time of, what's his name? Hildegard. So that's it for number one and number two. And Kush can now explain number three.
Okay, so as Ivy so very nicely explained. Okay, so we had the two formula for time of Brunhilde. So we know that Brunhilde is 2L over B because we let t equals 1 to make it simple. So here's number 3. So now the question asks us to find the time of Brunhilde. How old will each of the twins be upon Hildegard's return? So basically they're asking us to find the time, how much time Brunhilde experiences and how much time Hildegard experiences. So we know that time Brunhilde experiences is 2R over B because we let C equals 1. So now they give us the value that L is equal to 20 light years, and B is equal to 4 over 5. So if we plug it in, we find out the time that Brunhilde experiences is 50 years. Woo! Not that good. And then we also need to find the time that Hildegard experiences while she's on her trip. So if we go down here, we found from question number 2 that the formula for that the time Hildegard experiences is 2L over B times 1 minus beta squared. This is beta, not B. Remember that we left P for 1. So now obviously we already have the value, so from L, and we already have beta. So if we plug it in, we should get time of Hildegard is equal to, this is basically the, this part is basically the answer from time of beta. So this is 50 years, so this would be 50 years times. So, and then if we plug in beta here and then simplify this out, this will come out to 3/5. So the time that Hildegard experiences is 30 years. Now this leads up to what is a paradox, and then so this will be explained in question number 4 by Ayush. Good luck, man.
Okay, part 4 says, well, okay, so we can, for relativity, we can go either in the frame of the guy stationary, Brunhilde, or we could have looked at it with respect to the moving person, Hildegard. So how would these two be different? They would be different because there's actually 2 different motions with the 2 frames that we look at. With Brunhilde, the person is stationary, so he does not move, he doesn't have any acceleration, and that's known as an inertial reference frame. And Hildegard, however, he has to change direction when he comes back, which means he has to have an acceleration for him to change direction. And when he changes direction, if there's acceleration, that makes this equation invalid because you're going to have a changing velocity, and so you would have to calculate for each time that each velocity that it goes through. So and that when there's acceleration, it's known as an inertial reference frame. I mean a non-inertial reference frame. And the correct one is the non-inertial, the inertial reference frame, the one where the person is stationary, because that way you're not, because then you can use this equation, and you wouldn't have to do it for each individual velocity. So so this is correct. Brunhilde would be 80 years old because right now he's 30 years old. So where's Brunhilde? Show yourself 80 years old. And Hildegard, his twin, would be 60 years old.
Hildegard is 60.
Yeah, I'm 60.
Okay.
So basically, for part 2, question 1, we know that from the previous problem that Brunhilde's time is Hildegard's time, which in this case is tau, over the relativity factor, which is 1 minus beta squared, because beta is the fraction in speed of light that Hildegard's traveling at. So using that formula, we can take the derivative very easily. It is dt equals d tau over the factor 1 minus beta squared square root a. But we have to find d tau, so we have to rearrange this. So that would be dt times the factor.
All right.
Yeah, explain how. It's like
Okay. Yeah, we'll explain how. So this is part 2 of the paradox problem, and it was given that dt is the time of the inertial frame, and dt the very small amount of time in the inertial frame, and d tau is the time that it will take for the frame that accelerates. So that's d tau. So for part A, we just found d tau, which equals dt times the square root of 1 minus beta squared. So for part 2, it's asking like, what if we wanted to know the proper time of an accelerating object that starts and ends at the same point as an inertial observer? So like, how can we get this like mathematically? So we know that d tau equals dt and square root of 1 minus beta squared. So for this equation, like this equation works when velocity is constant, because we need to use the velocity. However, in this equation, velocity is not constant, because its velocity keeps changing in direction and perhaps even in magnitude. So we have to integrate this, the equation that d tau equals dt times 1 minus beta squared. So if we integrate this, we are able to integrate d tau, because that's just tau. However, if we cannot integrate dt and square root of 1 minus beta squared, because beta is not constant. It's the velocity that's changing because the object is accelerating. So we basically just leave it for now, because we haven't learned how to do this. So we just leave it 1 minus beta squared dt, because we know beta is changing and that dt is also a very small amount of time. So basically, this is the answer for if you want to know the proper time of an accelerating object. And just remember that this is the proper time of the accelerating object. This is not the time of the initial observer. That would be a whole different problem. And now Ayush is going to explain how we might test this experimentally if we had all the resources.
First, I just want to comment on this. If you wanted to integrate this, you could separate the integral into separate components, one where there's acceleration, one when it's constant. So then you can just plug in, using kinematics, you can plug in an equation for beta. It would be, you would use v sub o plus at for v, and then you just plug it in. So you can do it that way. So how could we test this experimentally with infinite resources? Well, particle processes happen very quickly, and well, in electric and magnetic fields, it's possible to have a particle go in a perfect circle, so we can measure the we can measure a particle when you have a magnetic field. It's like, say it's going this way. And when it goes in, it's possible to have a perfect circle. So we can measure the acceleration that happens there. We can calculate it theoretically, because it's a perfect circle. And then there's also things called atomic clocks, which measure very accurately the decay of certain elements. And so in order to test this, we could have an atomic clock set up here, and you would have say an element that's decaying, and when it decays, it releases certain ions or protons or electrons, and the electrons it would be in a magnetic field, so then it would go in a circle. So then we can calculate the exact time for each one, because we can use the atomic clock, and we can compare it using the reference frames that the times that we calculate using the time dilation equations. Then we can compare them, and when we compare them, they should be equal, and that's how we test this experimentally.